Welcome back to lesson 5.1 on congruent and similar triangles. And in this video, we're going to go through some examples of similar triangles. So, here's our first example. State if the two triangles are similar. How do you know? So, in this one, we've got all three sides labeled for both triangles. And we have to match up the matching sides. So we can do that by trying to match up the angles. We can see angle B and angle G are the same. So we would actually have to flip one of these triangles around, and we could redraw it that way. But I matched up the sides. The other strategy, if you know the side lengths, all the side lengths of both triangles, the smallest side length in the small triangle will correspond to the smallest length in the larger triangle. So here we've got 8, 12, 14. So 48, 72, and 84. Well, 48 and 8 have to match up. 72 and 12 would have to match up, and 84 and 14 would have to match up. So in this case, we're going to try to solve this using side, 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 meaning all three sides should have a common ratio or common scalar that the smaller triangle sides are multiplied by in order to give us our larger sides. So if the triangles are similar, then all of the sides will have a common scalar. So once I match up my sides, I'm just going to put them in a ratio with the side lengths of my larger triangle in my numerator and the side lengths of my smaller triangle in the denominator. So 84 and 14 are a matched pair, so we're going to do 84 over 14, and that should be equal to 48 over 8, which should also be equal to 72 over 12. And we'll just divide each one of these. And when we do that, 84 divided by 14, if we do that on our calculator, it should give us 6. Same with 48 divided by 8, that should give us 6. And 72 divided by 12 should give us 6. So we can see here 6 equals 6 equals 6. This is true. So our common scalar is 6. And that means that these are similar triangles, and we use side, side, side to prove it. All right, so that's side example number one. Let's go through a couple different examples. All right, so in this one, find the lengths of M and N. And what you might want to do here, I've matched up the corresponding sides, and we can see this angle A and angle E are equal. So that tells us a little bit about how we can organize our triangles. Um, we'll also go through and we can see which side lengths are going to correspond with one another. If we rotated angle or triangle ABC, if we rotated that about 180 degrees, it would line up perfectly with triangle CDE. So and we can see that because angle A and angle E are the same. So we match up our sides. That means 5 and M are a matching pair, 6 and 4, and N and 3. So at this point, maybe pause the video, see if you can prove that it is, in fact, a similar triangle, and find the lengths of M and N. All right, so let's take a look at our answer here. So, really, we're assuming these are similar triangles, and assuming that they're similar triangles, we're going to use the properties of similar triangles to find out the lengths of M and N. And the first thing that we're going to do is match them up. Vertex A and vertex E are equal, and we know that because it tells us that these two angles are the same. That smiley face in both angle A and E mean that they're the same. So then that means vertex C and vertex C are going to be equal. So those are going to be equal angles. Vertex B and vertex D. So if we rotate angle ABC 180 degrees, it would look almost identical to angle or triangle CDE, with the exception of a triangle CDE would be a little bit larger. So what we're going to do is we're going to set up our ratios for our sides. And I want to set up one of my ratios where I know the lengths of both of my sides. And in here, that would be line AC is going to be matching to line CE. So I know the lengths of both of those. The length of my larger triangle is 6, my smaller is 4. And then I can use one of my other matching sides. And so there's multiple ways we can do this. We could just do 6 divided by 4, find out what our scalar is, and then multiply that by 5, and that would tell us what m is. So let's go through and see if that works. And I just made a mistake there because 5, of course, is my larger triangle. So it'd be m times whatever that scalar is equals 5. The other way we can do it is we'll just do it step by step. So on my right hand side, I'm just going to do 6 divided by 4, and I'll get 1.5, and that's equal to 5 over m. Multiply both sides by m just to get rid of that m on the denominator there, and that's going to eliminate our fraction. So m times 5 over m, the m's are going to cancel out. We'll just have 5 on the left-hand side. And on the right-hand side, we're going to have 1.5 times m. Last step, we need to divide both sides by 1.5, and that'll tell us the side length of m. And when I do 5 divided by 1.5, I'm going to get 3.33. If you're working with fractions, instead of getting 3.33, you would have got 3 and a third. Both answers are quite acceptable. So we found out our side length for m, and now we need to find out the length of n. So all I'm going to do is, if I go back up here, I've got 3 times 1.5 equals n. And that's because I know that the side length in my smaller triangle 3 corresponds to the side length in my larger triangle n. So I'm just going to take 3, I'm going to multiply it by our scalar of 1.5, and that's going to equal n. And I can show that up at the triangle here. We see 3 is my small triangle side, n is my large triangle side. So my scalar multiplied by my smaller triangle side will give me the length of my larger triangle. So in this case, 3 times 1.5 is going to give us 4.5. And so that's the side length of n. So the lengths of m and n are m equals 3.33 and n equals 4.5. All right. So 2 good examples there. Let's do a third one. Are the following 2 triangles similar? How do you know? All right. So here, what we're going to be doing, if these 2 triangles are similar, then the 2 corresponding sides must be in the same ratio, multiplied by the same common scalar. And Our angle, our contained angle between those two sides must be the same, 76, 76. Perfect. So if I rotated this angle here, or this triangle here, UVW, and I rotated it around, it would match up with vertex V would be equal to G. Vertex U and F are the same, and W and H are the same. So my corresponding sides, I can get those here. UW is going to correspond to HF. UV is going to correspond to GF. The other way I can do that is I can look, okay, in my smaller triangle, which is my smallest side? Well, that's UW. So it has to match up with the smallest side in my large triangle, which is HF. And then, of course, that means the other side, UV, has to match up with FG. So we're going to put our ratios in here for our two sides and see if we have the same common scalar. And so here, 42 divided by 18 should equal 21 divided by 9 if these are similar triangles. We know the contained angle is the same, so we just have to prove those two sides are in the same ratio. So 42 divided by 18 it's going to give us 2.33. And 21 divided by 9 is also going to give us 2.33. So our common scalar here is 2.33. And by the properties of SAS, a side angle side, we know that these are indeed similar triangles. All right, one more example here, and we're going to use a word problem this time. So, here's our example. A statue honoring Ray Hinachin from 1934 to 2002 can be found on Spadina Crescent East near the University Bridge of Saskatoon. Use the information below to determine the unknown height of the statue. So we can see here we've got a person who's 1.8 meters tall, and they create a right angled triangle at this point here. And this angle is going to, these two angles are going to be the same in this. When you have a perfect reflection, so say this is bouncing off a mirror, the beam of light coming straight down would reflect back at the exact same angle. So that angle and that angle are the same. But for purposes of this, we don't necessarily need to know that. We're just going to assume that these are similar triangles. And if they're similar triangles, then that means that side length 2.4 here and side length 4 meters here must be matching sides. And this height of 1.8 meters will correspond with the height of X, our statue. So we're going to use our common scalar here. We know that 4 divided by 2.4 will give us our common scalar here. And then once we have our common scalar, we're just going to multiply 1.8 by our common scalar. And that's going to give us the height of the statue. So 4 divided by 2.4, if we put that in our calculators, we should get 1.67. If you're using fractions instead, this would be 1 2/3. Now, we're going to use that common scalar to find the height of the statue. We're going to take that scalar, multiply it by the height of my smaller triangle, which is the height of the person, 1.8 meters. And that is going to give us the height of the statue. So in this case, 1.67 times 1.8 is going to equal x. Put that into our calculators. we're going to find out that x is 3. And if you notice here, our units of measures are m for meters. So the height of the statue is 3 meters. All right, so there's 4 examples on similar triangles and using their properties to solve for heights in other similar triangles. I hope you enjoyed that. If you have any questions, please let me know. And join me for our next lesson on the Pythagorean theorem. Take care.